So asymptotes typically occur with rational functions. That is, say f of x equals p of x divided by q of x. So that is a polynomial. So is the denominator. It's a polynomial such as a quadratic function, cubic function, and so forth. So a vertical asymptote is a vertical line along which the function goes toward positive infinity or negative infinity. This happens when q of x equals 0, i.e. the denominator is equal to 0. A good example, we've seen this before, f of x is equal to 1 over x plus 2. If we graph this, at negative 2, we will have an asymptote. The reason being, when we plug in negative 2, the denominator would become 0. Horizontal asymptote is a horizontal line along which the function approaches 0 or a fixed value. A fixed value of y. And if f of x is equal to p of x divided by q of x, a polynomial divided by another polynomial, the horizontal asymptote is the x-axis, i.e. the line y equals 0 if the degree of the numerator is greater than the degree of the denominator. The horizontal asymptote is the line y equals c, where c is the ratio of the leading coefficients of p of x and q of x occurs when the degree of p of x and q of x are the same. We have seen that the limit at infinity and an infinite limit are not the same. I've mentioned this before. In this problem, what we are looking at is the limit at infinity. So what happens as x approaches infinity? Prior to applying or finding the limit, let's see if we can factor the numerator. I can factor the numerator as x, let's see. Could we think of two numbers so that when we add, we get -6, and when we multiply, we get 1. Well, that's not going to be feasible. So look at the polynomial x squared minus 6x plus 1 divided by x squared minus 9. So the degree of the numerator and the degree of the denominator are the same. So the limit as x approaches infinity is approximately equal to x squared over x squared. The rest don't matter. So that would give us 1. Another way of looking at it, if you pull x squared out of the numerator, we have 1 minus 6x over x squared plus 1 over x squared divided by x squared 1 minus 9 over x squared. So limit x approaches infinity, x squared times 1 minus 6 over x plus 1 minus x squared divided by x squared times 1 minus 9 over x squared. So those two would go away, and x is approaching infinity. In other words, it is becoming an extremely large number. And I'm dividing 6 by a large number here in 6 over x, so that is going to become 0. I am dividing 1 by a large number because x is approaching infinity. So in 1 over x squared, as x approaches infinity, that is going to become 0. Same argument applies for -9 over x squared. That would become 0. So we end up having 1 minus 0 plus 0 divided by 1 minus 0, which is 1 over 1, we get 1. So we want to evaluate the limit as t approaches infinity, square root of t plus t squared divided by 2t minus t squared. So I have a common factor of t squared. We can't use the trick that we used in the previous problem. Have 1 plus square root of t is simply t raised 1 over 2 divided by t squared. Entire thing divided by t squared times 2t over t squared minus 1. T squared would go away. Limit x approaches infinity. 1 plus t raised 1 over 2. If you bring it to the denominator, you will have t squared times t raised -1 over 2. And the second case, we have 2t, 2 over t minus 1. So the limit t approaches infinity, 1 plus 1 over t raised 3 over 2 divided by 2 over t minus 1. So since t is getting larger and larger, 1 divided by a large number is going to go toward 0. And we have 2 divided by a large number as t goes to infinity, so that would become 0. So the limit is simply 1 over negative 1. We end up getting negative 1. You could always verify your answer with the help of a calculator. So what we have here is square root of t, I'll put x, plus t squared or x squared divided by 2t minus t squared. I'm going to put x squared. Make sure you put parentheses properly, and let's graph it. And you can see the curve in the bottom is going toward infinity along the line y equals negative 1. So it's going that way. So y equals negative 1, which is the dotted line here, is the limit, and that would be the horizontal asymptote. In the previous problem, the horizontal asymptote was the x-axis. Oh, no, it was y equals 1. So y equals 1 was the horizontal asymptote. So we want to evaluate the limit t approaches infinity, square root of t squared plus 1. Now, anytime we are looking at t approaches infinity or x approaches infinity, we are looking at the limit at infinity. So pretty much we are looking for the horizontal asymptote. Now, how do we go about this problem? So as t approaches infinity, the value of 2t squared would be greater than 1. So I could approximate it and write it as limit t approaches infinity, square root of 2t squared, which is simply limit t approaches infinity, square root of 2 times square root of t squared. Square root of 2 times t. Square root of t squared is simply t. So the limit here as t approaches infinity is infinity because t here gets larger and larger as t approaches infinity. So limit t approaches infinity, square root of 2t squared plus 1 is infinity. Approximately equal to infinity or just infinity, they are one and the same. So it doesn't matter. Okay. We are trying to find, well, let's go ahead and graph the previous one. Square root of x, or square root of 2x squared plus 1, and we graph, and you can see it is going toward infinity as x increases. So the curve is of that sort. So as x keeps on increasing, the value of y increases, and it is going toward infinity. But that is not a horizontal asymptote in this problem, because it is not going along a horizontal line. So I'm going to pull e raised to x out of the numerator. So we have 1 minus e raised negative 2x divided by e raised to x, and e raised to x, 1 plus e raised negative 2x over e raised to x. Those two would get cancelled. Limit x approaches infinity. I'm going to move the e raised to x to the numerator. It becomes e raised negative 2x divided by 1 plus e raised negative 2x times e raised negative 2x. So limit x approaches infinity, 1 minus e raised negative 4x divided by 1 plus e raised negative 4x. We know that if we have e raised x, then it is a growth function. It is an exponential that grows, and it is going to grow toward infinity. But if it is negative, if we have e raised negative x, it is going to decrease, and it is going to go to 0 rapidly as x increases and goes toward infinity. So since we have two negative exponents, both that as well as that would go to 0, and we would end up having 1 over 1, which is simply 1. Let's see if that is true. You could always verify your answer using a calculator. Divided by parentheses are important. And you can see it is going toward 1 as x approaches positive infinity. But if x is approaching negative infinity, the answer would be negative 1. So that you can look at the picture and get the answer. Here is another example involving a trigonometric function. So as x approaches infinity, a trigonometric function is periodic. So I could write it as sine x over, divided by x squared plus 1. So no matter what value of x we pick, sine x is something that goes like that. In other words, it is a number. So, and if I square, and that number is going to be between 1 and minus 1. And if I square, the numerator is always going to be a value between 1 and negative 1. So the upper limit and the lower limit would simply be 1 squared. There is a theorem called squeeze theorem, and it is going to come in chapter 3, I believe. But here I'm going to use this without the squeeze theorem. So the numerator is going to be some small number. Let's just say it is going to be 1. The denominator is x squared plus 1. As x approaches infinity, x squared is going to get larger and larger. So we are dividing a number which is 1 or less than 1 by an extremely large number, which is infinity. So 1 over infinity would be 0. Let's see if that is true. So what we have in the numerator is sine x squared divided by x squared plus 1. Have to be careful here. Have to adjust the window. So you can see that as x approaches infinity, the value would approach 0 on the x-axis. Let me zoom further here. Perhaps I can set the axis 0 to 0.2. And you can see it just drops down to 0. And lastly, we have limit x approaches infinity, ln of 2 plus x minus ln of 1 plus x. So using the properties of logarithms, that would simply be ln of 2 plus x divided by ln of 1 plus x. We know since ln is a continuous function, we can move the limit inside and we will have x plus 2 over x plus 1. And that is a rational function where the numerator degree and the denominator degree are one and the same. So that limit is simply equal to 1 over 1, so which is the leading coefficient of x, or the numerator and denominator polynomial. So we have ln of 1 over 1, which is ln of 1. We know ln of 1 is 0. Let's see if that is true. So ln of 2 plus x, so we could use double parentheses here, or we could simply do ln of 2 plus x minus ln of 1 plus x. Let's check our window. We can't have a negative number, and let's put between 0 and 10 graph. Oh, that drops to 0 really rapidly, so let's reduce that to 2, and you can see it's slowly moving toward 0. If I increase to 10, so by the time it gets to 10, it rapidly becomes 0. And if we adjust the y-axis and change it to 0 to perhaps 1.5, you can see it is dropping down towards 0 rapidly. So the limit here is simply y equals 0, or the horizontal asymptote is the x-axis.